All right, so we're going to look at now what's called the modulus, the conjugate, and then we'll also look at division of complex numbers. So this is lecture 31 of 95 lectures on Specialist Maths Units 3 and 4. Some prior knowledge to understand this lesson will be Introduction to Complex Numbers. So that was lecture 30, which was the previous one. So I'll put that link below. It also will be helpful to understand Introduction to Vectors. So that was lecture 19. And for this video in particular, it will be helpful to have seen a certain part of a logic and proof lecture, which was lecture 9, particularly about the idea of a converse of a statement, of a mathematical statement. So as always, I'll put those links below. The key concepts we'll cover in this video though are the modulus of a complex number, the definition of a complex conjugate, properties of that new idea that we're going to introduce of what's called the complex conjugate. We'll then look at what's called the partial converse of the conjugate property. Now that part took me forever to wrap my head around because that's definitely the most challenging part of this video. So we'll look at a proof of that. And then in previous videos, we defined addition, subtraction, and multiplication of complex numbers, but we didn't do division. But once we learn a few of these ideas, we can then do division. So it all hopefully will tie together. So let's jump into it and look at what's called the modulus of a complex number. So the modulus of a complex number, I don't think is a particularly challenging idea, I hope. So just recall the idea that we can have this complex number essentially as a point in space on our what's called Argand diagram. So if that's unfamiliar, go and watch the previous video. But remember that our sort of Cartesian plane is now what's called an Argand diagram, where on the x-axis we have the real component of the complex number, and then on the y-axis we have the imaginary component of the complex number. If we want to find what's called the modulus of the complex number, we use these absolute value signs, so two straight lines. If we want to find the modulus of z, we're essentially just finding the length of the vector that would point from the origin to that number. So in the example we have here, we have that the complex number z1 is 3 plus 4i. Now 3, remember, is the real part of the complex number, and 4 is the imaginary part of the complex number. So it's sort of sitting at this point here. And then we know that this is a nice Pythagorean triple. We're just basically finding the length of the hypotenuse. So the square root of 3 squared plus 4 squared is the square root of 25, which is just 5. So you'd say that the modulus of z1 is just 5. It's basically the length of this blue line. Same deal over here. If we had negative 3, 4, then this would be also have a length of 5. So we'd say the modulus of z2 is also 5. Okay, from that we can deduce a few properties of the modulus. One of them is that if we take the modulus of z1 multiplied by z2, that's the same thing as taking the moduli of z1 and multiplying by the modulus of z2. So just following this property here. Similarly for the quotient, so if you're to take the modulus of two complex numbers divided by one another, it's simply the modulus of the first one divided by the modulus of the second one. This third idea here is what's called the triangle inequality. And it basically just says that the modulus of z1 plus z2 is always less than or equal to the modulus of z1 plus the modulus of z2. I'll put a link below to explain that in more detail because I have explained that concept before. But just briefly here, let's think. We always know basically that if we were to add, if you think of it as three sides of a triangle, z1 and z2, if you were to add z1 and z2, that's always going to be greater than or equal to the absolute value of the hypotenuse. Let me explain that a little bit differently because I think that wasn't very clear. Let's just imagine that we've got imagine this was our complex number and it was just the real number 3. And then we've got some other complex number that's sort of just this length here. We know basically that this length is always less than or equal to these two lengths added together. So that's what's called the triangle inequality. But again, I'll put a video in this part of the video to go and check that out if you're curious about that. Let's look at defining now what's called the complex conjugate. So again, we've got some complex number, a plus bi. The conjugate is what we call z bar, and is defined as a minus bi. So essentially all you do is you negate the imaginary component of the complex number. So let's see what that looks like as an example. Let's look at this orange arrow here. This is the complex number z1, and you can see the real component is 2. The imaginary component is -3. If we were to negate the imaginary component, we would get 2 plus 3i. So in sort of dashed orange here, we can see that z1 bar is 2 plus 3i. One sec. All right, so z1, this is the conjugate. Z1 bar is 2 plus 3i. Similarly, if you've got some other complex number, -1 minus 4i, then the complex conjugate of that is -1 plus 4i. So hopefully you can see that to take the conjugate of a complex number has the effect of reflecting it across the real axis. Remember, the real axis is the x-axis. So yeah, that is what it means to take the complex conjugate. Now what we're saying now is we're going to look at a bunch of properties of the complex conjugate. So one of those properties says the following. It says that the conjugate of a sum is the sum of the conjugates. So let's break that down with this diagram a little bit. It's basically saying if we take z1 and we add z2 and then take the conjugate of it, that's on the left-hand side here, that's the same thing as the conjugate of z1 plus the conjugate of z2. So let's explain that in a bit more detail. Let's look down here. We take z1 and z2. If we add them together, let's see what we get. We're going to get, if I do this the right way around, if we take z1 and add z2, remember when you add vectors together, you sort of do tail to tip and then add them like that. Similarly, we're going to add z1 to z2 over here. And we're going to get something like this. So that's sort of visually showing the addition of those vectors, right? Now let me show you a few things. If we were to say, I think you would agree that z1 plus z2, remember vector addition is commutative, so it doesn't matter which order we do things in. So z2 plus z1, same thing as z1 plus z2, is this black vector here, right? But what's really cool, you'll notice, is this vector down here, I think you would agree, is z1 plus z2. Now, I think I just heard myself. I think before I didn't say it's the conjugate of z1 plus the conjugate of z2. Okay, if we add the conjugate of z1 plus the conjugate of z2, we get this vector here. But if we just add regular z1 and regular z2, we get this z1 plus z2. Now what this property is saying is if we take the conjugate of z1 plus z2, so if we were to take the conjugate of this, it's the same as this. And I think you would agree, you can see that they are in fact reflections across the real axis. So the conjugate of z1 plus z2 would get you up here. So we can see that the sum of the conjugates is equal to the conjugate of the sum. So hopefully that picture sort of clarifies things a little bit. All right, let's look at a few other properties of the complex conjugate. Okay, the next property is this. Basically says if you take the conjugate of z1 multiplied by z2, that's the same thing as the conjugate of z1 multiplied by the conjugate of z2. So sort of similar situation to addition, but now it's using multiplication. So in words, we could say that the conjugate of a product is the product of the conjugates. Okay, so let's maybe look at an example here to make some sense of it. So let's imagine our complex number z1 is 2 plus 3i and z2 is 1 minus 4i. So Z1 is in green here, Z2 is in blue. Okay, Z1 multiplied by Z2, if you recall from the previous video, how to multiply complex numbers, you'll get something like this. And it's sort of at this point, I'd encourage you to sort of pause the video and crunch the numbers. You'll get this last term with an I squared in it, but you know that I squared is -1. So you get that 14 minus 5i. So Z1 multiplied by Z2 is 14 minus 5i. So that's sort of a complex number that's sitting over here somewhere. Okay, so now let's think about this property. The conjugate of Z1 is Z1 bar. So that's this green dashed one down here, which is 2 minus 3i. And the conjugate of Z2 is 1 plus 4i. Okay, multiply them together, doing the same process, you'll get 14 plus 5i. So you'll notice that that's this one up here, 14 plus 5i. So when we multiply the conjugate of Z1 by the conjugate of Z2, we can see that it's equal to 14 plus 5i, but I think you would agree these two red, the sort of solid red arrow and the dashed red arrow are conjugates of one another. So what we can say is if we were to take the conjugate of Z1 multiplied by Z2, conjugate this whole thing, it will get you up here. So that is sort of a visual demonstration, hopefully, of the fact that Z1 multiplied by Z2, taking the conjugate of that, is the same thing as taking the conjugate of Z1 multiplied by the conjugate of Z2. And so that's sort of our second property of the complex conjugate there. Okay, let's have a look at another property. Okay, this one's a little bit more straightforward. Again, we've got some complex number. The property of the complex conjugate is that k, where k is some real number, multiplied by z, taking the conjugate of that is the same thing as k multiplied by the conjugate of z. So again, let's just make an example. Let's say k is 3, where k is just some sort of scalar multiple, scaling up and down our complex number, and z is 2 plus 4i. Okay, we can see that if we take 3 multiplied by 2 plus 4i, we take the conjugate of that, that's the same thing as 3 multiplied by the conjugate of 2 plus 4i. So you get this situation going on. Again, pause the video and check it out. But you'll see in either case, 6 minus 12i is the conjugate. Okay, so obviously we can scale that up and down, right? So k doesn't have to be 3, but you get this situation going on where it doesn't matter what value k is, that multiplying it by a scalar, the conjugate of a scalar multiplied by z is the same as the scalar multiplied by the conjugate of z. It's a mouthful, but hopefully that makes some sense. All right, let's look at the next thing. Okay, another property of the complex conjugate is that z bar, so the complex conjugate multiplied by the complex number itself is equal to the magnitude of is equal to the modulus of z squared. So again, let's look at an example. Let's say z is 3 plus 4i, and therefore z bar is 3 minus 4i because they're conjugates of one another. Okay, multiplying them together, just sort of doing sort of algebra expansion of a binomial, you'll get 9 minus -16, which is 25. And so that's it. That's essentially it. We know that the modulus of z is 5. We know that the length of this line is 5. And then if we square it, we get 25. So it's basically just saying the same thing. Just to summarize, taking the conjugate of a complex number, multiplying it by itself is just equal to the modulus of that complex number squared. And so sort of visually here, if you multiply this by this, you get a real number, 25, has no imaginary component. It's just the modulus of the complex number, and then you square it. So I think that's an interesting property of the complex conjugate as well. It's sort of shown here. Okay, hopefully making some sense. Okay, the next one's interesting as well, or more interesting, I think. If we take some complex number and we add its conjugate, we get 2 multiplied by the real component of that original complex number. So again, let's look at 3 plus 4i. We know that the conjugate will be 3 minus 4i. If we add them together, we're going to add the real components and add the imaginary components. In this case, we'll get 3 plus 3, which is 6. 4i minus 4i is 0, so you just get 6. We know that the real component of z was 3, and you can see that 6 is just 2 times 3. And so that you get that, therefore z plus z bar is 2 multiplied by the real component of z. Okay, that might be a little bit confusing algebraically. Hopefully it's not, but maybe graphically it'll make more sense. If you take some complex number z and you add its conjugate, now remember, vector addition, it doesn't matter where it starts in space, right? So remember, the complex conjugate is a vector that points at this point down here, right? But if I just sort of move that up and shift it up to the tip of z, then it's going to be pointing here. Adding the vectors together through some vector addition, you get a point sitting at the point 6 here in this case. But you can see how that would hold for any... you would see how that could hold for any complex number. So I didn't realize I had an animation here. So this is the number. This is the complex number represented as a vector. If we then add the conjugate to it, it's going to look something like that. And then we get that this here is the 2 multiplied by the real component of the original complex number. Okay, on to the hardest part. Maybe pause the video here and have a read of all this, because this can be quite challenging, I think. It took me a while to wrap my head around this. Algebraically, I think it's not too bad, but for some reason I just found it difficult to wrap my head around. In any case, let's look. So what we're talking about now is proof of the partial converse of the conjugate property. Okay, I'm just going to talk through this and then we'll explain what's going on. So let's imagine again we've got some complex number, a plus bi. Got some other complex number now, which is c plus di. Okay, b and d are not 0. So b and d are not 0. So that means that z and w are complex numbers. They're not real numbers because b and d is not 0. Okay. If we take z plus w, so we add this and this, we'll get a plus c plus b plus di. But we know that z plus w is real. Why is that the case? All right, apologies. What we're trying to show, I should have said, is that w is the complex conjugate of z, okay? And we know that if w is the complex conjugate of z just from before, that when we add z and w, we're going to get a real number. So that must mean in this case that b plus d is 0, because this part, the imaginary part, must go to 0. In which case, d must be equal to negative b. If that goes to 0, then d equals negative b. Okay, and so when we multiply them, we also know from the previous property that we'll get a real number. So we take a plus bi multiplied by c minus bi. But we know that so z by w, so z is a plus bi by w. All right, w is c plus di, however, d is negative b. So it's a plus bi multiplied by c minus bi. Okay, expanding that out, or I should say rather multiplying these together by expanding, you'll get this. Okay, but we know that zw is also real. So we have that bc minus ab must equal 0 because the imaginary part goes away. So therefore, Yeah, we can take b out as a factor. So b multiplied by c minus a equals 0. But we know that b is not equal to 0. So therefore c equals a. Because this part must be 0 because b is not 0. So c minus a must be 0. So therefore c equals a. And so we have shown that w is in fact the complex conjugate of z. Now, it's confusing. Well, I find it confusing. But let me explain in more detail. Basically, what it's saying is we've got some complex number z. If w is its conjugate, then z plus w and zw are real numbers, which is some of the properties we spoke about before. But you'll notice if we change things, that's not always the case. And let me just pick it so we can see the values. Just want them to be in view. All right, so we've got something like this, where z plus w and zw are not real numbers because z and w are not complex conjugates of one another. So for example, z is 3 plus 0y. Sorry, I just realized this is wrong. This is 2 plus 1i. Okay, when z and w are not complex conjugates of one another, we get that z plus w and zw are not real numbers. So now let's think about why it's called the partial converse, and I think this can be quite tricky. So thinking back to some of the logic that we've spoken about before, so a converse of a statement essentially reverses the if and then components of the original statement. Okay, so our original property is that we've got some complex number z, and we know that z multiplied by z bar and z plus z bar are real numbers from what we've spoken about in the other properties. Okay, the converse of that statement would be that z multiplied by z bar and z plus z bar are real. So if they are real, then w is the complex conjugate of z. But that is not always true, because if we were to set the imaginary components of the complex numbers to 0, we can see that if, let me pick better numbers here, we can see that if z and w are real, entirely real, no imaginary component, that w is not the complex conjugate of z in this instance, but z plus w and zw are only real. Essentially, this is just the situation of 2 plus 4, which is 6, and 2 times 4, which is 8. But that's an instance where the converse doesn't apply. If z and w are entirely real, then w is not the conjugate of z, but z plus w and zw are real. So that's why it's called the partial converse. It only holds under certain conditions. That's what I've found very hard to wrap my head around. Okay, so yeah, the proof is a partial converse. It applies only under certain conditions, that z and w are complex, not entirely real. And the result holds only when both zw and z plus w are real, not in all scenarios. So hopefully that made some sense to you. But yeah, basically, if you take the complex conjugate of a number, you take a complex number, take its conjugate, if you multiply that conjugate with the complex number, you'll get a real number. If you add the complex number with its conjugate, you'll get a real number, but the reverse isn't always true because you could just have 2 real numbers. Anyway, that's my understanding. Curious what you think about that. Let me know. So that's just that last idea there. Okay, very last thing, division of complex numbers, not to be understated. This is very important. So to define division, let's multiply our complex number by 1, but we write the number 1 as a minus bi divided by a minus bi. So as we should say first, we're going to take the reciprocal of our complex number. So we do 1 over a plus bi. And what we can do is we can strategically multiply that by the conjugate over the conjugate. So we're going to take 1 over bi multiplied by a minus bi over a minus bi. Multiply the fractions, you'll get something like this. Okay? So essentially what we're showing is that this is the reciprocal, is 1 over a complex number, right? So more generally, for two complex numbers, if we need to divide them by one another, we know that if we've got two complex numbers, z1 divided by z2, that's the same thing as z1 multiplied by the inverse of z2. But the inverse of z2 is this business. Okay? If we recognize that this top part is the complex conjugate, so z2 bar is the complex conjugate, and then this part here is the modulus squared. Remember, the modulus is the square root of a squared plus b squared. If we square that, we get just a squared plus b squared. So you can see how now we've defined division for complex numbers using this inverse property. I just want to explain that in more detail because it's a bit confusing. Think of this as being separated. It's z1 multiplied by the inverse of z2, and the inverse of z2 is defined as this. Remember, z2 is just some other complex number defined as a plus bi. So to take the inverse of that, it's a minus bi divided by a squared plus b squared. So then you end up with this as the division of z1 divided by z2, as long as z2 is not equal to 0. Okay, here's an example that explains things in more detail. So z1 is 3 plus 4i and z2 is 1 minus 2i. Follow the steps out here and you'll get negative 1 plus 2i if you divide z1 divided by z2. So we can see that this is how things are actually set here. z1 is this number, z2 is this number here. z1 divided by z2 gets you to negative 1 plus 2i, so it gets you over here somewhere. I put these sliders in just to sort of show division. I don't think it shows anything particularly exciting, but I'll leave that up to you to decide if this visual representation of the division says anything to you. But I just thought it was cool that we could sort of show where those complex numbers go. So remember, what we're doing is we're taking z1 divided by z2, and that gives us this resultant complex number over here. I don't know, I'm not sure there's much we can say about it. It is what it is, but kind of cool as a bit of a graphic to look at. Okay, that was challenging, I thought. Let me know how you get on, and good luck with all your studies. I'll talk to you soon. If you found this at all useful, give us a thumbs up and pass it around so that other people can find it useful. All right, I'll see you later on.